The screen is visible to you, na? As well as my voice is audible. Yes or no?
Yes, sir.
Okay. So far what we have studied Blick's theory and Kosla's theory and Lenz theory, right? So for Blick's theory, there was one limitations that Blick assumed the horizontal and vertical creep to be equivalent. So he did not multiply any parameter by any weightage factor. So this particular limitation was corrected by Lane, right? And from that particular correction, we got Lenz theory. So in Lenz theory, there was a multiplication of 1 by 3 for the horizontal creep, right? So in this way, the Lenz theory was being developed. Similarly, there was another uh, assumption by Bleek that I think everybody can remember that there was one assumption made by Bleek that the seepage of water follows the outline of the substructure, right? Means the percolation of water happens in close contact with your substructure material. I think everybody know that. So what do you mean by that? If this is your wire, suppose this is your impervious layer, you have the piles here, right? So water, what will be the nature of flow of water? It will come down like this in close contact with the substructure, right? In this way the water percolation will be happening and the water will come out from here, right? So this one was an assumption made by Bleek, and this is a limitation also, because if the percolation of water of the seepage that does not follow this profile, practically it does not. This was one assumption made by Bleek, but this particular assumption is not correct because the water profile is not like this. The water won't be following this particular track. So what is the track followed by water? Water follows like this, somewhere like this, and it comes out like this. Okay, everybody getting the point? Yes or no? Hello? Okay. The others are not listening or what? Riyanka? Sukant? So the water follows this particular profile. Okay, basically this is rather this is the practical one, which is not satisfied by Bleek's theory. So from these limitations, the Khoslas theory was developed. In this particular Khoslas theory, the water profile, means the profile followed by the percolating water uh, takes up this path. The path is this particular way. So similarly, there will be a not particular, this will only be the okay. So this particular, this won't be the profile that will be followed, right? There will be many such lines, means a few water particles will be moving in this way. Similarly, few will be moving just below that in this way. So there are many such tracks being followed by the water particles. So practically this happens, and this was being developed by means this particular theory was developed by Khosla. Okay, so you can see that this Khosla's theory, he designed the wire accordingly. Accordingly means taking this particular flow pattern, he designed the wire. So generally this Khosla's theory is being used to develop the concrete wires, you had three types of wires, right? One was rock fill wires, another one was vertical masonry wires, right? And this one is and the last one was concrete wires. So this particular theory, that is Khoslas theory, this particular theory was used for the designing of your concrete wire. Okay, so look, if phi is the flow potential, suppose there is the flow potential means the nature of flow. Okay, so phi being a function of x axis, x and z means the x axis your abscissa and your z axis your ordinate, those two are the parameters. That is, if it is dependent on those two parameters, then d2 phi by dx2 plus d2 phi by dz2 equal to 0. Phi is the nature of flow or the flow equation. Okay, so phi is the a function of x and z, where you can understand that x is the movement along x axis, x this particular x term, and z is the movement along z axis, right? So if phi can be represented as a function of x and z, then this particular phi, this value will be taking up, means it will be utilizing your Laplacian equation. That is, you have studied in mathematics, I think, that Laplacian equation means d2 phi by dx2 plus d2 phi by dz2, that is equal to 0. So this is the Laplacian equation. That means if you solve this particular equation, okay, if you solve this particular equation, then we will be getting the phi values taking the boundary conditions. That is your this percolation of water cannot start from within, right? It cannot start from within, it has to start from outside your floor, outside the impervious floor, and it has to end not within the impervious floor. So this particular boundary conditions, if applied, means it can, there won't be any percolation happening here, right? So if these boundary conditions are applied, so if you integrate these values taking all the boundary conditions, then the phi, the function that you will be getting, phi equal to a function of x and z, that particular phi value will give us the flow pattern. Okay, we will be getting many such phi values, and that will give us the flow patterns. Okay, so if you solve this particular equation, we will be getting the flow patterns, where phi is the potential flow potential, and that can be represented by k into h, and h is your head. You already know that is the residual head at any point within the soil. Okay, and k is the coefficient of permeability of soil. So solving this equation, we can get the phi values, and that will help us to get, if you see the next slide, this particular phi, this particular all the lines, these are the solution of your phi values. We won't be getting any particular solution, we will be getting number of solutions. If we just put the solution of this, if we just solve this particular equation, we will be getting plenty of phi values. Okay, and those number of phi values represented in this way will give us such lines, it will give us such curves. You can see that all these particular lines are solution to those phi values. I think everybody is clear with that. Okay, so now just concentrate on these two terms, that is streamline and equipotential lines, and your flow net, these particular terms. Okay, so what do you mean by streamline? Streamline is basically the line that is followed the path that is followed by your water particle while percolation. Means suppose this particular concentrate on this streamline, so there will be a movement of water particle from this point. It will be just following this particular path, and it will come like this, and it will emerge out from this point. Similarly, another water particle will be following like this. So these roundabout, these horizontal curves are known as streamlines. Okay, so streamlines are basically, you can see that streamline represent the paths along which the water flows through the subsoil. So these horizontal curves are known as your streamlines. Okay, so the path, their streamlines are basically the path followed by the water particles. This is known as streamline. Next point is that you can see equipotential line. What do you mean by equipotential line? Look, these are this kind of vertical curves. These are the vertical curves, right? Similarly, these all are vertical curves. So these particular curves are called as equipotential lines. Why these are known as equipotential lines? Suppose for a particular curve, if you are inserting piezometer, right? If you are inserting piezometer along that particular curve, then in all the piezometers we will be getting the same head of water. Look, this particular curve, just concentrate on this. Okay, we have inserted piezometer, 3 piezometers along this particular curve. So you can see the head of water is same for all the 3 piezometers. So basically along the same equipotential line, if you insert a piezometers all throughout the curve at that particular line, not only if you insert a piezometer here on this curve, it won't be the same, but along the same equipotential line, if you insert piezometers, then the head of water will be remaining the same in all the piezometers, right? So these particular lines, so this is one equipotential line. Similarly, if we concentrate on this particular line, if we insert a number of piezometers along this particular line, then we will be seeing the head of water in those particular piezometers will be remaining the same. So this will be termed as an equipotential line. Similarly, here also, these are all equipotential lines. Okay, so you can see that an equipotential line represents the joining of points of residual heads, of equal residual head. Okay, similarly, AB is also an equipotential line. AB is also an equipotential line. If you insert a few piezometers here, you will see that the head of water, you can see the head of water here is the same, right? It is the same. So the AB is an equipotential line also. Okay, so you can see that, look, this is your wire. This is your wire, right? These are streamlines. Right, these are streamlines. What are the equipotential lines? Suppose there are piles being constructed like this. So what are the equipotential lines? It is roundabout like this, right? Similarly here also. So you can see a somewhere net like structure has been developed, right? You can see that a net like structure has been developed there, right? Here I am telling about here. So this kind of net like structure, as it is known, as you can see this, it is net, kind of net look alike. So this particular part is known as flow net. You can see that a net has been formed by the intersection of equipotential lines and streamlines, and this particular net thing is known as flow net, that is being described by Khosla. Okay, so this is known as flow net, and the area inscribed between two subsequent streamlines and two subsequent equipotential lines, the area being developed due to the intersection of two equipotential lines and two streamlines, that particular area is known as your field. So you can see that, suppose, okay, just see that this is one streamline, right? This is another streamline, and this is one flow net, this is another flow net. So the area inscribed between these two is this particular area. So this will be termed as a field. So this particular part will be called as field. Okay, so just refer to this diagram. You can see that this is one streamline, this is another streamline, these are two equipotential lines. So the area is inscribed between the two streamlines and two equipotential lines is known as field. And this complete flow pattern, the net type thing is happening out here. So this is known as flow net. Okay. Till now, tell me if anybody is having any problem. Yes or no? Everything is clear till now? Okay. So this is known as flow net. Okay. So this was basically the theory being adopted by Khosla, and basically this particular theory is used to design your concrete walls. And the first two theories, that is your Bleak theory and length weighted creep theory, those two are used to design your vertical drop wires and your rock fill wires. Okay, so this particular theory is used to design your concrete wire. Next thing you need to understand the two terms, that is your exit gradient and critical exit gradient. What do you mean by those two? So look, here they are, suppose concentrate on a soil particle here. The soil, what are the forces acting on those particular, these are the streamlines, right? There is movement of water from here to here. It is being given by this arrow mark, right? You can understand that. So suppose you concentrate on a soil particle in the substructure. Okay, suppose there is a particular soil particle here. So what are the forces acting on that particular soil particle? You can see that the forces are due to the flow of water. There is a tangential force being applied due to the flow of water, right? This is the wire. So suppose this is a streamline, right? The flow is of water is happening like this. Suppose there is a soil particle out here. Okay, so in what are the forces that will be acting here? One will be a tangential force like this, that is being forced by the flow of water. So there will be a force like this, right? And also there will be a force of self weight, that can be denoted by Ws. So the self weight of that particular soil particle will be there, and also there will be a disturbing force, or you can say the force that is because of the flow of water, and that will be acting in tangential direction along your tangential direction to that of your flow pattern, right? So if you resolve this particular f value into two vectors, then what we will be getting? We will be getting a horizontal force like this and a downward force like this, right? If you resolve this particular force vector, all of you know that suppose there is a force vector like this. If you resolve it into two components, we will be getting it two forces like this on resolving into two components. right? So similarly, if we resolve this particular force that is being applied by the flow of water into two components, we will be getting these two particular forces, right? So look, up to the round about the center of your wire, the force is acting downwards. This particular force, if you resolve it, just neglect the horizontal component, it has nothing to do with the stability of the structure, okay? So just cross this horizontal component out, you just concentrate on the vertical component. Up to the center of this, the vertical component will be acting downwards like this, but when you go towards the upstream side of it, suppose the soil particle is here, then the force will be acting like this, right? So if you resolve it into two components, the vertical component will be acting like this towards the upward side, and the self weight will always act in the downward side, right? It will be acting always in the downward side. So for the stability of the structure, in order to resist the failure due to piping, what we need at this junction, the value of this particular component, suppose you just write it down as Fv, okay? So this Fv, everybody is getting it or not? This Fv should be less than your self weight of the soil. If it is not the less than your self weight of the soil, then what will happen? This will just allow the soil particle here to pop out from the structure, right? It will just allow the this particular soil particle to pop out, because the upward force is acting more towards the upward side, so the soil particle will get disturbed, and as a result there will be a piping failure. So in order to restrict the failure due to piping, the F value, look at the end, just concentrate on this figure. Look at the end, your F value will be completely, there won't be any horizontal component, because here if you draw the tangential line, this F value will be vertical itself, right? There won't be any horizontal component. You can understand that, right? So this particular F value, if you resolve it into two vectors, there won't be any horizontal component, so the complete F equal to will be Fv at this particular end. At the end it will be F equal to Fv, and so this force will be acting, and this particular your self weight force will also be acting. So this F value should always be less than your Ws value, in order for to stabilize the particular structure, or you can say that in order to resist the piping failure, this should be the case, okay? So you can see that the just consider on the blue line, the for the soil grain to remain stable, the submerged weight of soil grain should be more than its upward disturbing force. I have told you, right? So you can understand that and the disturbing force at any point is proportional to the gradient of pressure of water at that particular point. So what do you mean by that? At this suppose at this particular point, your disturbing force, that is F, should be proportional to gradient of pressure, that is dP by dl. So at any point, suppose the disturbing force here is F, right? So this F value should be proportional to dP by dl. Similarly everywhere, for this particular point also, the F value here, that will be proportional to the dP, that is the pressure here, dP by dl, the pressure here divided by the length of the particular, means the incremental length, that is dl. So F is always proportional to dP by dl along that particular streamline, okay? So that is known as, you can see that the disturbing force at any point is proportional to to the gradient of pressure of water at that particular point, which is represented by dP by dl. Okay. So the gradient of pressure, that is dP by dl, at this particular end, at the exit, you can see this is the exit, this is the entrance, right? This is the entry and this is the exit. So at this particular point, the value of dP by dl, the value of dP by dl, that will give us the exit gradient. So at the exit, the gradient of pressure will be termed as exit gradient. Okay, I think everybody is clear with that. So at the exit, the gradient of water, the gradient of pressure will be termed as exit gradient. And what do you mean by exit, critical exit gradient? Suppose the value of F is such that F is equal to, if suppose the value of F, if is equal to your the weight of the soil particle, means the submerged weight or self weight of the soil particle, such that the F value, the disturbing force, that value is equal to your downward force. What is the downward force? The self weight of that submerged soil particle. If this criteria is there, then the pressure, the gradient of pressure, the value of gradient of pressure will be termed as critical exit gradient. So if the value, if this value, generally what will consider this case, F should be less than your Ws. For this consideration, the gradient of water at the exit, that is dP by dl, considering this scenario, okay, so this particular value, that will give us the exit gradient, okay, Eg. And considering this particular case, F equal to Wg, the value of dP by dl, that will give us the critical exit gradient, Ceg. Have everybody understood? Just let me know. The difference between your exit gradient and critical exit gradient. Any problem you can ask me. If you have any problem in understanding, you can ask me. Okay, if you have any problem, you can ask me later on also. Okay, so you can see that this exit gradient is said to be critical when the upward disturbing force on the grain is just equal to the submerged weight of the grain at the exit. So considering that scenario, that is F equal to Ws, the value of your pressure gradient will give us the critical exit gradient, that value. Okay, so for in order to we will be providing one factor of safety for designing your wire. So what will be the factor of safety? If you know the critical exit gradient, then your exit gradient will always be less, because your F value should be less than, look, this F value, this F value for Ceg, that is your critical exit gradient, is always greater than your F Eg, right? That is, for exit gradient, the F value will be less than your critical exit gradient F value. So for that, what we do, we will find out this particular value, that is your critical exit gradient value will be finding out, and then we will be multiplying it by a factor of 1/4 to 1 by 5. Will be multiplying this value by a factor of this, that is your FCEG. So this particular value will be multiplied by a factor of 1 by 4 to 1 by 5, and that is known as your factor of safety. So why it is done? You have done in design of RC design, steel structural design, everywhere you have, for design purpose you have multiplied by a factor of safety, and that is used as a safety factor, right? So similarly here also the exit gradient will be equal to 1 by 4 to 1 by 5 times of your critical exit gradient value. Okay, so just look at that. All of you know that this is the derivation. All of you know that the submerged weight of unit volume of soil can be given. This you have studied in soil mechanics. I think you already know that. So the WS, that is the submerged weight of a unit volume of soil, that can be given by your gamma W into 1 minus n into SC or SS, anything, minus 1. Okay, this is the value of WS. You have studied in soil mechanics, where gamma W is the unit weight of water, SS is the specific gravity of the soil particle, and N is the porosity of the soil material. So this WS is given by this particular formula. Okay, so at the critical condition, your F should be equal to WS, right? I have already told you that. Okay, so you can see that F equal to WS. Okay, so what is the value of F? F equal to dP by dl. I have already told you, dP by dl. Okay, so you already know that P equal to rho G into H, right? And here rho means rho W, because the pressure is being applied due to the pressure of water, right? So rho value is the rho W. So this particular rho WG, that is equal to gamma W into H. I think everybody know that, right? So P can be represented as gamma W into H. So if you take the derivative at both the ends, if you differentiate at both the ends, okay, so what will be getting? dP equal to d of gamma W into H, right? This particular value is constant, this is constant, so there won't be a change in this particular value, so that will be equal to gamma W into dH. So dP can be represented as gamma W into dH. So dP by dl you can see that, right? dP by dl equal to gamma W into dl by dH by dl. Okay, so this F can be represented in this way. Similarly, similarly not WS is given by this particular formula only. You can see that it is being given by this particular formula. So if you cancel out the gamma W at both the ends, then dH by dl, you can find out that dH by dl can be represented as 1 minus n into your SS minus 1, where n is the porosity of the soil material and S is the specific gravity of soil. And this particular just let me know whether you have understood or not till now. So the solution of phi value I've already told you that phi needs to be solved out. In order to get the flow lines and your equipotential lines, this phi need to be solved out from this particular equation, that is d2 phi by dx2 plus d2 phi by dz2 equal to 0. So solution of this gives us the phi value, and we have to apply the boundary conditions as well. Okay, so this particular solution is very cumbersome. Okay, so that is more of mathematics is needed in order to solve this particular equation. You can understand that this is quite complicated. The Laplacian equation means the solving of those is very difficult. So it can be done by the mathematical part. You can see that it can be done mathematically, but it is cumbersome, and also an electrical analogy method can also be used, but both of them are very much complicated. So what Khosla did, he introduced a comparatively very easy solution to this. How he introduced? He named that method as method of independent variables, and he broke the complete structure into a number of parts. What are the parts? We will see to it in our next class. Okay, so what are the parts? It has been broken to it has been broken, this particular wire has been broken into a number of parts. Okay, and this analysis of those individual simple components has been carried out, and from that the result has been we have got the results. So this particular method is known as your method of independent variables. So Khosla, he broke the complete wire into a number of different parts which are independent of each other, and he analyzed all those various parts, and he calculated the result accordingly, and superimposing all the results, he got the actual result. So this particular theory we will be seeing to it that it is known as the method of independent variables. In our next class we will get details of it. Okay, so if you have any problem you can ask me. If you have any problem you can ask me till now.